Hi, in this session, I want to give you an introduction to hashes. When many people think about cryptography, they think about encryption, being able to make something secret and then being able to get access to it again. But one of the most helpful tools in cryptography is actually called a hash, which is not encryption. My goal in this session is not to give you a real detailed overview of all the mathematics or operations that occur in hashes, but frankly, more to specifically give you an idea of what they're used for. So let's jump in and let's get started. First, let's just start with what encryption would be used for. If I've got something that I want to keep confidential and I'm going to send it to somebody else, I'm going to send that over a network. And if I have an attacker that can get in the middle and see that, then it's a problem. So what I do is I take and I encrypt that message across the network, and then that attacker can't see the contents of the message. So I basically take and do an encrypted pipe or whatever method I'm going to use, and I'm able to hide that from the attacker. In addition to wanting to keep something secret, I may also want to make sure that the message hasn't been changed. So let's look at an example of this. If I'm sending that message across the network, and let's say that I want somebody to sell 500 shares right away because the market is collapsing and I need that to happen. But all of a sudden, in the middle of the transmission, there's some sort of network noise that occurs. And that changes the message so that it's not intelligible. And the receiver says, I'm not sure what to do with this. And maybe in this particular case, they wouldn't take action and they wouldn't sell those shares, which would be a problem. But you can see that if you have network noise that causes any sort of a change in the message, you want to know that there was a problem with the message so it can be resent, and that you make sure that you get the right information. And another example of this is if it's not network noise, but instead when a message is sent, let's say that I as a sender say, hey, transfer $1 million over into this other account of mine. But in the middle, I've got an attacker that when I'm sending that message, they actually change the message and it says transfer $1 million into this particular Swiss bank account. Well, the receiver says, okay, well, you just sent me this message, appears to be all okay, so I'm going to go ahead and do that. It's done. Well, obviously, you turn around and say, wait a minute, where did all my money go? So what we want to talk about is how do we take and deal not just with confidentiality, which I've talked about in some of my other sessions, but specifically talk about integrity. And so if you look at confidentiality, that's really ensuring that only authorized parties can see information. Integrity is detecting when information has been modified or corrupted, right? Whether on purpose or by accident. And you can, frankly, in many cases, you will use both of these together. And there's one other aspect related to integrity, and that's verifying the identity of the sender of information. That's called authentication. Now, we're not going to spend much time talking about authentication in this session. The basics that we'll give you about hashing we'll talk about in the future or use in the future in a future session to talk about authentication and some of the ways that that's facilitated. Here, what we're going to talk about specifically is integrity and how hashes can help with integrity. So let's take a message. Let's say that somebody has said, hey, I'm going to make a commitment to send you $1 bazillion. And if English isn't your first language and you start looking up what a bazillion is, you won't see what it means. It just means a lot of money. So somebody's going to send me a lot of money. And so they sign it a very generous person. You might say, well, they're probably a crazy person, but we don't need to get into that right now. But what we want to do is we want to make sure that that message, when it arrives, that it is in fact the message that was sent, right? And so what we do is we take that message and we break it up into its binary components. And so what I'm doing here is I'm just showing you that each one of these letters and characters is represented by a binary number, which in this particular case happens to be ASCII or UTF-8. And so what we would do is we would take that entire message and look at the representation of it in binary form. And then once we've done that, then we can take and say, okay, so we've got all of this in binary. Now, the first thing that happens when we want to take and ensure the integrity of a message is we're going to take and we're going to break it into blocks. And you can see that I've broken these into 4-byte blocks, 4 8-bit character, 8-bit bytes. And here you can see that there is a a remainder, or the last block is only 2. So what we'll do is we'll actually pad that to ensure that all the blocks are the same size. Now we take and we collect all of these blocks together, and then what we're going to do is we're going to perform an operation on them. Now in this particular case, what I'm going to do is I'm going to perform an integrity check with a checksum, which is frankly a very primitive hash, if even you could call it a hash, but it'll be a very simple way for you to understand this concept, and then we'll kind of build up from there. So I want to do a checksum, and we're going to use a very specific type of checksum called a longitudinal parity check. Basically what this does is just XORs all of the blocks. And for those of you that aren't familiar with XOR, it's an operation where you take two binary digits and you compare them, and if they are the same, then the result is 0. If they're different, then the result is 1. So you can see here, I've given examples. If both of the digits are 0, then the result is 0. But if one of them is 1 and one is 0, then the result is 1. And then finally, if both of the digits are 1, then the result is 0. So what we're going to do is we're going to set up our little XOR machine up here at the top. We take our first block, and there's nothing to XOR it with, so it just goes right up there into the little XOR machine. And then what we're going to do is we're going to take the next block, and we're going to XOR that with this first block. Now, you can see that this changed, and what I want you to do is when I do this next one, watch where this value takes and converts to 0, as we see here. And this next digit will convert to 1 because this is a 0 and this is a 1. So I'm going to go ahead and click here, and you can see that this is a 1 and this is a 0 now. And what we do is we continue to do this with each of these blocks. We just XOR it with the last result. And with each one of these, we'll go and keep doing that until we get to the very end where we have the final checksum for that particular message. And with that, then we can come back to that message and we say, okay, now let's go ahead and let's place that at the bottom of the message so that when we send that the receiver of the message, they can take and they can perform their own checksum, do the exact same operation, and then they can compare their result with the checksum that was included at the bottom of the message that was sent. If they're not the same, there's two possibilities. Either something here in the message got changed, or the checksum got messed up in transmission. But either one of those says, okay, we're going to need to resend the message. Let's make sure that the right message gets through. Now, what you see here is this is really basically a primitive hash. You'll often hear hashes called fingerprints or thumbprints because it's basically kind of a summary representation of a message. It's a very valuable one because it allows you to know if anything in that message has changed, unlike a thumbprint or a fingerprint where, if I lose my left arm, my right thumbprint is still the same. It doesn't change. But in this particular case, if I change anything within that message, it's going to go ahead and change the result. Let's come back to encryption versus hashing and just make sure that that concept is correct. When I have a message and I'm going to encrypt it, I'll take and I'll have an encryption key, and I put the message through the encryption algorithm using that encryption key, and I come up with some gobbledygook, the result of the encryption. But I can take and turn around and using that same key, or if it's an asymmetric algorithm, the corresponding public or private key, I can go ahead and decrypt that message and get back to the same message. With a hash, on the other hand, when I take a message and I put it through a hashing algorithm, I can't come back to that message. That's actually a very important property of any hashing algorithm. Is you want it to have what I call the Hotel California effect. If you're familiar with that song, you can check in, but you can never leave. So that's how I like to think of hashes. And so here what you've got is if you have a particular message that you've hashed, you want to make sure that you can't come back and determine what the original value was. It's actually a very important aspect of any hash algorithm is you want what's called pre-image resistance. You don't want the receiver of a hash or the viewer of a hash to know what the image that created that was. So you want pre-image resistance. Now there's some other aspects that you want in a hashing algorithm. Another aspect is that you want to make sure that if you have somebody that takes and says, okay, this is the message that I want sent, and that turns into a hash, you want to make sure that an attacker can't create another message that results in the same hash. That's not good. And so if basically you have two messages that are not the same, then you'd never want the hash of one of those messages to be the same hash as the other message. And this is called second preimage resistance, basically saying, I don't want to be able to find a second preimage that matches that same hash. Now, finally, there's one more particular angle or attack that you want to be able to resist, and it's called a collision resistance. Here, what you have is you have an attacker who can actually form the original message. So they can actually take and craft that message in such a way that it results in a certain hash, and then turn around and craft another message that results in the same hash. And this is called collision resistance. Again, you don't want this to ever be able to happen. And so anytime that a hashing algorithm is being designed, you're really looking to make sure that it can meet each one of these particular criteria. And over time, what's happened is there's been an evolution of algorithms. It started with the very simple checksums, which, as you can see, were very simple and definitely not conforming to the preimage resistance and the collision resistance, etc. So over time, what's happened is that the level of sophistication has increased over time. So the next set of algorithms were called cyclic redundancy checks. If we take and we look at kind of increasing levels of sophistication, there was something called MD4, which was quickly replaced by MD5. Then you had SHA-1. You may have heard of SHA-2 now, and most recently SHA-3. So what we've seen is this evolution over time. Now, I've shown you what a checksum looked like, and that was a very simple checksum that we used. Now, as we've gone forward and each one of these algorithms has gotten more sophisticated, the operations that they perform are frankly quite complex to take and even draw out. But on Wikipedia, if you go and you look for SHA-2, you'll see that somebody's done an illustration, which is actually quite helpful. Frankly, you still need to be able to take and analyze it to understand everything. But it talks about how the hashing operations take place, and a message is broken up into blocks, and then each one of those blocks is actually put through this sort of operation. In the case of SHA-2, it'll happen 64 times, where it takes and mixes each block through a set of these operations, and then uses that as the intermediate hash. They'll take the next block, do the same thing, and they keep taking and going through each block until they've completed that. Now, in this session, my plan is not to try to explain to you exactly how SHA-2 works. That would take a bunch of time, and it would kind of go into a level of detail that we don't want to try to address here. So let's come back and let's look at each one of these algorithms and kind of the timeline and such. So MD5 has a result of 128 bits. It was created in 1992, originally by Ron Rivest, and then it was actually codified in an RFC after that. Then we had SHA-1, which was created in 1995. It increased the length of the result. So if you remember, I had a result with that checksum, which was 4 8-bit components, which basically is 32 bits. Now we've seen that this goes up to 128 bits, 160 bits. SHA-1 was codified in RFC 3174. And then what we saw was SHA-2, which basically took and expanded the options and really the level of sophistication of the hashing algorithms. And so SHA-2 in 2001, there were 3 variations, basically very much related to each other, of the SHA-2 algorithm. Then later, there was a smaller version, the 224-bit version, SHA-224, that came out in 2004. And then in 2012, there were some modifications so that the 512-bit hash could result in a 224 or a 256-bit result. Now, in terms of the RFCs, I'll just kind of put these out. The first RFC has SHA-224 in it. Then you have an RFC that basically took and codified all of SHA-2. And in addition to this NIST codified the SHA-1 and the SHA-2 algorithms in a document called FIPS 180-4. Now, following on this, NIST realized that SHA-2 was over time going to see some weaknesses, and so they actually created a competition, had people submit their different designs, and one of those designs was adopted and codified as SHA-3. It's codified in FIPS 202. So what you see is kind of an evolution of hashing algorithms, the sophistication, the lengths, providing you some different options for lengths, with the longer lengths being more secure or considered more secure. Now what I want to do is I actually want to show you how to create a hash with OpenSSL, just to make this as real as possible. What we're going to do is I'm here in this directory called Intro to Hashes, and within here I've created this file called file to hash. So we'll just look at that real quick. And you can see that it has that same message that I'd shown you earlier. Now, what we want to do is we actually want to take and use OpenSSL. So I can't type and talk at the same time. So we'll go ahead and we'll say OpenSSL. Then we say that we want to create a digest, which is a different name for a hash. Now, in this particular case, let's start with an MD5 hash. And then we're going to say, I want to create an MD5 hash of the file to hash file. So when I do that, it will give me a result that you can see here, and this is that 128 bits. Now, if I take and I change this to SHA-1, right, with that file to hash, you'll see that I get a different result. It's a longer one because this one's 160 bits. And then what I'm going to do is let's go ahead and we'll take and do a 256, SHA-256, and show that. And you can see, again, this is a much longer result. This is a 256-bit result. So what you can see here is with OpenSSL, you can very easily create a hash and get some idea of how these hashes work and such. So what we're going to do now is we're going to switch over here. And I just want to talk a little bit about some of the uses of hashes. One of the important ones is integrity, making sure that you know when a message has been corrupted or intentionally changed. You can also use it for authentication via digital signing. And as I mentioned earlier in this session, we're not going to talk about digital signatures and authentication. In this session, I plan on doing a separate presentation on digital signatures, just so that we have enough time to cover that topic. And another one is password protection and using hashes to actually protect passwords. And I wanted to actually spend a little bit of time just talking through this, because it'll give you an idea of anytime that you enter a password, how that's being protected. Now, as we start talking about password protection, I probably earlier should have mentioned some other hashing algorithms that have been created specifically for password protection. One of them is called bcrypt. There's another one called scrypt. And these use a slightly different methodology for hashing, which actually slows down the hashing process, and it's actually to prevent attackers from being able to take and easily recreate hashes. So in this particular case, let's say that I've got a password. I've made it my big fat password with an exclamation mark. So that's my password. And what I'm going to do is I want to protect that so that other people can't see it. So this is typically when you take and you enter a password into a particular website, instead of storing the actual password, my big fat password, as you see here, in plain text, what the website will do is it will actually put that through an algorithm, such as bcrypt, which will take and mix it up, basically create a hash with something called a salt. And I'll explain in a moment why a salt is used. But ultimately, what will happen is that will result in a hash value that can be used. And then, so this is when I register, I'm going to do this. And then if I log in and the website wants to confirm my password, they're going to have me enter my password again. And they're just going to basically do the same operation. They're going to use bcrypt, that algorithm, To create a new hash, they need to use the same salt because when they create the hash, they want to make sure that they're putting in the same initial values. And then what they can do is they can just compare these two to make sure that they're equal. And if they are equal, then I've entered in the correct password. Now, by doing this, what happens is that if there's a particular attacker who gets onto the website, gets access to all of the password files, right? They're going to get a whole bunch of hashes, which because bcrypt has preimage resistance, they won't be able to turn around and turn those back into the password. They can't go backwards from this hash, right? This is just a bunch of gobbledygook that doesn't enable them to easily do that. Now, there have been attacks where instead of attempting to take and go backwards, what an attacker will do is they will actually take and create what's called a rainbow table, where they will take and hash a whole bunch of possible passwords and then see if those hashes match to a value that they have, that they have found on a particular website. And this was very broadly done for a long time. And this is where algorithms such as bcrypt really started to provide the ability to add a salt, which means that if an attacker got onto one website and they were going to analyze it, they would have to create an entire rainbow table using that same salt. And so if the same salt was used for all the passwords, they have to do that. But what most of the algorithms and implementations of bcrypt have now gone to doing is actually using an individual salt with each password that they hash. And by virtue of that, an attacker would have to take, and for that particular salt, they would have to create a rainbow table over and over and over for every one of the passwords, which makes it very difficult. Now, this doesn't necessarily protect you if you have a very weak password, because they're probably going to be able to guess that. But these types of algorithms really help. And I want to give you one other example. Let's say that I want to encrypt a file. If you've ever used, for example, pkzip or some of these other little tools that allow you to encrypt a file with a password, let's just look at how that works. So here I've got this particular file that I want to encrypt. And what I do is I take and I enter in a password, and pkzip, for example, will take and create a hash of that, same way that we just showed you. But then that hash is actually used as the cryptographic key that is used to encrypt that particular file. So what I can do is I can generate, using a password and a hashing algorithm, I can generate a cryptographic key. And it's a symmetric key. So basically what happens is that I take the original file, I use this particular symmetric key to encrypt the file. I end up with a bunch of gobbledygook. Now, if I want to decrypt that file, what I'm going to do is I'm going to enter in the same password later. The pkzip or whatever tool is going to take and say, okay, well, let's start by creating a hash of this. So it takes and hashes that. Should come up with the exact same value, right? Assuming that everything that was entered in was the same. And then because this is the key that was used to actually encrypt, then that same key can be used to decrypt. But that key is only available at the time that decryption is going to be performed, because it's being entered by you as the user saying, I want to decrypt this. And the tool says, well, hold on a second. I don't have a cryptographic key. Can you go ahead and give me something? So hopefully all of this has provided you a better understanding of what hashes are, what they're for, some of the likely uses. In future videos, I hope to be able to cover some additional uses of them. We may talk about TLS, we may talk about digital signatures and those sorts of things in future videos. And hashes feature very prominently in both of those cases. So thank you very much for joining, and have a great day.